In 15.6, we're going to talk about an idea and some skills that are really important down the road. They're really going to come in handy. So let's make sure we focus in on this one. The I can statement today is I can solve. So let's write the word solve right here. I can solve for a variable in a literal equation, also known as a formula. So we'll talk more about those in just a second. The warm-up says match each description with its formula. So what I'm going to do is I'm going to read over here on this side and on the left side, and then we're going to take a look at the right side and see if we can figure out which one it is. What I'm hoping is when you read it and when we talk about this, you automatically have these formulas come to mind because we've used all of these before. They should be things that you're very familiar with and know just off the top of your head. So it says slope-intercept form of a linear equation. I'm hoping that one, everybody should know that one. That's y equals mx plus b. So we'll come down here and find that one, and we'll just draw a line and connect those. Next one, distance between 2 points. We've done that before. That's the big square root and x2 minus x1 quantity squared and stuff like that. So that's this one. Match those up. And then slope between 2 points. If you're just talking on a graph, you might be tempted to think rise over run, but we won't find rise over run here because when you're finding the slope between 2 points, it's the y2 minus y1 on the top over x2 minus x1. So that's this one here, just right straight across. Area of a triangle. Triangle, that's 1/2 base times height. Got to know these. These are going to come up a lot in the future. So let's find 1/2 base times height. That's this right here. Then we've got area of a triangle. Now, area is measured in square units, so that's one way that you can keep the two formulas with a triangle straight. So circumference is 2 pi r, and area is pi r squared. So they both have a 2, they both have a pi, they both have an r. But this is the formula that we're looking for right here. Area of a circle is pi r squared. Okay, again, square units for area, so r squared on this one. So let's go ahead and draw this line here. Circumference of a circle is next. We just talked about that one. It's the only one with a C on it, so that's a dead giveaway, but you ought to know that formula. It's one you get memorized and keep memorized. So circumference of a circle there, and then area of a parallelogram. If you need a quick reminder, remember a parallelogram just has two pairs of opposite sides that are parallel. So it looks like this, and the base is this distance right here, and then we don't do this slanted height right here. We go from top to bottom, so that would be h. So the area of a parallelogram is just base times height, so that's going to be this. Volume of a cylinder, suppose it would have to have a v in there, but remember a cylinder looks like this, okay, kind of like a can. We have to find the area of the base and then multiply it by the height. Well, the base is a circle, so that would be pi r squared, and then we're going to multiply it by h. That's this one right here, so I'm going to draw a line right there. And then volume of a rectangular prism. A rectangular prism is basically just a box. So what we're talking about there is basically these types of shapes. So that's going to be, we could say, area of the base, big capital B times h. But most of the time we just think of it as length times width times height. So that's going to be this guy right here. And then the Pythagorean Theorem, most people think a squared plus b squared equals c squared. I like to memorize it this way. Leg squared plus leg squared equals hypotenuse squared. So I've abbreviated it right here. That reminds you what type of triangle it works on. It works on a right triangle, and only right triangles have a hypotenuse. So we do a leg squared plus a leg squared equals hypotenuse. That's a squared plus b squared equals c squared. A and b represent the legs, c represents the hypotenuse. So we're going to draw that line there. And then an arithmetic sequence and a geometric sequence. Those finish it out. The only two that are not used are right here in the middle and then that first one right here. Remember, arithmetic sequences, they deal with the same common difference between each set of terms, whether it's positive or negative, getting bigger or smaller. So arithmetic ones, this is this one right here because we're going to be adding those. So we get a big mess right here. And then the geometric one's got to be this one right here. Again, common difference right here for arithmetic in this one, and then common ratio right here for geometric. So there are those formulas. All good things to have memorized because those will come up again. So a formula is sometimes called a literal equation. So a literal equation. Now, literal just means it kind of has to do with letters and words and stuff like that, okay? So you'll hear some people call them literal equations. Now, formulas, or the proper plural way to say this is formulae, A-E at the end there. So let me make that look right. Formulae. Now, enough people just say formulas that we can just say formulas also. So they're really helpful because basically here's what happens with a formula, okay? It allows us, so this is what a formula does, it allows us or someone else to do all the thinking and all the work to figure out a problem once, and then what we do is we just use the formula that comes from that thinking without having to start from scratch every single time. So it'd be kind of tough if you had to figure out or derive what the Pythagorean theorem was or the distance formula every single time. We figure it out once, and then we can use it in the future. Now, sometimes a formula is not arranged in the most convenient way, as you're going to notice in this example that comes up next. So I'm hoping that you know this one. I purposefully did not put it in the matching game up top, because this is one that comes up all the time. This is d equals rt. D is distance, okay? The speed is r, stands for the rate of speed, and then t is time traveled. Now, you can use an uppercase d or a lowercase d, it doesn't really matter, okay? So find the distance traveled if the speed is 50 miles per hour and the time is 4 hours. Now, this is one people just figure out in their heads automatically. They just say, oh, if I'm going 50 miles per hour for 4 hours, I end up going 200 miles, but here's why. The distance is equal to the rate, which is 50, times 4, which ends up being 200. Now, what a lot of people skip over is this. They skip over the fact that you can actually use the units to help you figure out how this problem works. So this is 50 miles per hour, and this is times 4 hours. So this is a really good exercise to go through. I want you to take a look at this. When we multiply these, you can cross-cancel units just like you can cross-cancel numbers. So I cancel the hours, and what's left is miles. So the only thing left as far as words go is miles, and then 50 times 4 is 200. So the answer on this one is 200 miles. This would be a much better way to write the answer. Now it says find the speed, or in other words, find the rate, if the distance is 5 miles and the time is 12 minutes. All right, so we're going to do the same thing here. We're going to do d equals rt, and on this one we're going to say the distance is 5 miles, the rate, we don't know what it is because that's the speed, and then this represents 12 minutes. Now, oops, let me write min here, so min, okay? Now, by putting the units on here, it's going to help us have the correct units on the answer. So what I'm going to do is I'm going to solve for r, so I'm just going to divide by 12 minutes, divide by 12 minutes right here. And what I end up with is I get r equals 5/12. Now, you could have just solved this and said 5 equals r times 12, divide by 12, and there's your answer right there. But this is a little bit richer right here because notice that we have miles on the top and minutes on the, minutes on the bottom. So what we could write is 5/12 miles per minute. Okay, so that would be one way to write the answer. Now, if you wanted to throw that in the calculator and get a decimal for that and round, that would be totally okay. It is a story problem, so that might be appropriate. And then it says find the time, so we're missing the time on this one, if the speed is 20 miles per second and the distance is 85 meters. Okay, so 20 meters per second and the distance is 85 meters. So this is the speed, so this is r, and this is the distance. So I'm going to do 85 meters equals, this is the speed, 20 meters per second, and then times t. Now what I'd like you to notice about this is, again, you could just do 85 equals 20 times t. We're going to divide by 20. Let's see, and then we'd reduce that and stuff like that. But I am going to grab the calculator for this one. So we end up with, let's see, 85, turn this on, get this to turn on, 85 divided by 20, and we end up with 4.25. Okay, awesome. Okay, so this is 4.25. So here's the deal though. If we just write down t equals 4.25, T stands for time, so we could figure out what time represents. But I want you to notice what happens here, and I'm going to show some work for this. This is a fraction, and it's a fraction in front of this variable that we're trying to solve for. So what I'm going to do is I'm going to multiply by the reciprocal. I'm going to multiply by seconds over 20 meters, and I'm going to multiply by seconds over 20 meters. And watch what happens here. The 20 meters cancels with the 20 meters, the seconds cancel with the seconds, so I'm left with t on that side. And then I've got meters here and meters there, those cancel, and I get 85 divided by 20, which we figured out was 4.25. But take a look at what's left. What's left is seconds. So the answer on this one, and we know time is measured in seconds on this one, but that can still help us there. Now, here's the point. When we're dealing with a formula, we use this formula 3 different ways. First, we found a distance, then we found a speed, and then we found a time. What happens is, this is not always the most convenient way to write, that particular formula. There are times where it might be useful to have it solved for r. So what we can do to solve for r, so I'm going to go ahead and keep this one right here. We wanted the speed in this second one. Notice what we did is we divided by the time. So I'm going to divide by t, so I get this. R equals the distance divided by the time. Okay, and that might be a relationship that you could be familiar with. Like if we travel 500 miles and it takes us 5 hours, 500 miles divided by 5 hours is going to be 100 miles per hour. The other thing we could do is we could say, look, maybe I want time all by itself. If I want time all by itself, all I have to do is trade here, and let's just divide by r. Time would be equal to the distance divided by the rate. Okay, and we can do each one of those formulas that way. Now I'm going to shrink this down just a tad, and we're going to come down here and we're going to take a look at these formulas. So I've got a couple on the front page and a couple on the back page. These are not too bad, but again, these are really, really useful skills. So it says solve each formula or equation for the indicated variable. So what you're going to get is you're going to get an equation. It may or may not be something that you're familiar with. These couple are. And then it will tell you which variable you want to solve for. So I'm going to zoom in on each one of these so that we can really take a look at the work that's going on here. And it says y equals mx plus b, and we want to get m all by itself. So the trick here is to think of everything in the problem except for that particular variable like a number. So we're going to think of it like this. I'm going to leave the m there. I'm going to say that y, I'm going to think of it like say a 7. And this is going to be an m times, let's say this is a 5, and then this is plus a 3. So I've replaced everything except for the m with a number, and then I look over here and say, oh, I know how to solve this. I would just subtract 3. I'd get a 4, and then I'd have m times 5, and we get rid of multiplying by 5 by dividing by 5. So I get an m on this side, and I get 4/5 on this side. This is really comfortable. This is not as comfortable, but it actually works out a little bit easier, and I want to show you how. The equivalent of subtracting 3 would be subtracting b. So those are going to cancel, and look at this. We have two different variable terms. They don't have the same variable, don't have the same exponents or anything like that, so they're not even like terms. So the only thing that we can do here is we just write y minus b. We're basically saying, look, I know you want me to subtract those, but I can't like I could over here when they were numbers. So now I have m times x. So we've got the equivalent of m times 5. What we did over here is we divided by 5. So let's do the equivalent on this one. Let's just divide by x. We want to undo multiplying by x, so we're going to divide by x. Those are going to cancel. Now, we normally flip these around, and this is one time where I say, okay, it's okay to flip these around. I'm going to write m equals y minus b over x. So the cool thing about this is we don't really have to do any math. All we're doing is just some equation solving, just using some algebra skills to rearrange stuff. So we're not working really with numbers, we're just doing some rearrangements here. So that's how you do that one. And I'm going to come over here and take a look at this right here. So on B it says we want to solve for y2. Well, y2 is this guy right here. So the first thing we notice, and you may remember doing stuff like this, let's go ahead and circle these because that bar right there is a grouping symbol. It groups the top together and the bottom together. So I want to get rid of the bottom. I want to get rid of dividing by x2 minus x1. So here's what I'm going to do. I'm going to multiply by x2 minus x1. Multiply this side by x2 minus x1. Okay? Now on this side, this entire factor is going to cancel with that entire factor. So we're going to have y2 minus y1 on this side. And then this gets a little bit interesting. On this, I could just write this as m and then x2 minus x1. If you wanted to distribute through, you totally could. That wouldn't be a problem at all. But here's what's interesting. The only thing that I have left is I just need to get this by itself. That's all I need to do. So the only thing I need to do now is just get rid of that minus y. So I'm going to add y1 and I'm going to add y1. Those cancel each other off. So what I get is y1 equals, y2, and then it equals all this stuff. We've got this term plus this term. Now, there's nothing that you can do there because they're not like terms. We can't add them together or anything like that. So I'm going to write down m and then x2 minus x1 and then plus y1. All right, and that's it. That's all you have to do. Okay, so we've got the y2 solved for, we've got it all by itself, we've got it isolated on one side, and we're finished with that problem. Now, that's not the only way to write it. One interesting thing about this is because there are so many variables floating around, there might be more than one way to write the answer. So if you saw somebody, you looked at your friend's paper, and you said, hey, what'd you get for this one? They may have done m times x2 minus m times x1 plus y1. And this might make it a little bit more clear that there's really no math that we can do here because there aren't any like terms or anything. So either one would be okay. There are lots of different ways to write that. Just make sure your math is solid on these. Okay, let's go ahead and take a look at the second page. One thing that's really tricky about solving formulas or literal equations is when the variable is in the denominator. So if we have to isolate that variable and it's in the denominator, if it's in the bottom, there's a couple of things that we run into that can be kind of tricky. So the first one is, how do we get the variable out of the denominator so we can solve for it? We really don't want to solve for something that's in the denominator. We don't want to solve for something on the bottom. Okay, and when should we distribute and get rid of parentheses and when should we not? And this is kind of what we dealt with on the last problem. So let's take a look at this one right here. I'm going to zoom in just a tad. And let's take a look at this. So you'll notice that D is in the denominator. Well, the very first thing that we've got to do in order to be able to solve for something is it's really tricky to solve for it in the denominator. So we need to get it out of the denominator. So here's what I'm going to do. I'm going to take this and I'm going to multiply it by D. And I'm going to take this side and multiply it by D. Now notice that we're in kind of a good habit of putting that second one in parentheses. So the second one has more than one term. That's really important. Okay, I'm going to go ahead and cancel the D here. So I get C on this side, and then I get D times A plus B. Now, this is in parentheses, and a lot of times we'll say the words quantity. So this is D times the quantity of A plus B. So if you wanted to, I suppose you could distribute through, but it actually would be easier if we just said, hey, look, this is D times A plus B. What if I just divided both sides by A plus B? Whoops, A plus B. I can cancel this factor with that factor, so then I end up with D and then C over A plus B. Really easy format. Now, if you didn't do that, if you made it look a little bit different, let's say that you distributed through, this would be dA plus dB. I want you to notice what happens here. We now have two terms with D in it. Okay? We don't want two terms with D in it. We only want to see one D on that side. So we definitely would not want to do that. So we don't want to distribute through when it creates more variables than what we want to solve for. So if you've got one D over there, leave it that way. Figure out a way to get rid of the other stuff on that side. So let's slide over here and let's take a look at the next one. So this one demonstrates a little bit different thing. The variable is in the denominator, but notice how it's hooked together with that one. So we're going to do the same type of thing that we did before. So I'm going to multiply by x2 minus x1 on both sides, so x2 minus x1. Now notice that because I'm multiplying by this quantity, x2 minus x1, I did put that one in parentheses also. I can cancel that factor off with that factor. So I have y2 minus y1, and then over on this side I have x2 minus x1, and then I'm multiplying that by m. Now take a look here. This is a completely different situation than what we had on the last one, because on the last one we had the D, the variable that we were trying to solve for, outside the set of parentheses. Okay, we had one of them over here, and now it's on the inside of the parentheses. So if it's inside the parentheses, we've also got to get it outside the parentheses so we can solve for it. So the lessons that we can learn from these problems here are, if the variable we're trying to solve for is in the denominator, you've got to multiply it by that to get it out. And the next thing is, if it's inside parentheses, you've got to distribute to get it outside those parentheses so we can actually work with it. So again, I'll zoom in on this one just a little bit and finish this off. So this is m times x2 minus m times x1. And again, if you wanted to write down the x1 times m first, there's really no good rule for how we're going to write these. You could do x2 times m and stuff like that. And then this side is y2 minus y1. Okay, this is the x2 that we're solving for. So remember, we want to solve for x2. So we want to get that variable all by itself. So I'm going to go ahead and move this one to the other side. I'm going to add m times x1. So add m times x1. So those will go away. So then I've got m and then times x2 equals y2 minus y1 plus m times x1. And then the only thing we need to do now is to get the the x2 by itself, is we want to get rid of the timesing by m. So I'm going to divide everything by m. Okay? So we're going to cancel those off, and I get x2 equals y2 minus y1 plus mx1 over m. All right, so that right there is a perfectly good answer. There is one other way that you can write this. I'm not going to go take the time to do that. We'd basically separate this into three different fractions and then try and reduce them. You'll notice that we couldn't reduce anything in these first two, but there is an m in this one and an m in that one. So there might be a case where you want to do that, but we're not going to do it on this problem right here. Okay, so let's take a look at this last little bit. There's only 3 more here. There are some interesting techniques that come from this. So we want to solve for x. So on this one, take a look here. This x is in the numerator, so that's good news. We're not dealing with a variable in the denominator anymore. But one way that we can think of this is we could think of this as m over k times x equals 7. So now we've got a fraction in front of the variable like we did on the front page. So I'm going to multiply by the reciprocal, k over m, multiply by k over m. The m's are going to cancel, the k's are going to cancel, so we get x equals 7k over m, and we're done. That's it, okay? Solve this one for x. Again, something interesting here. Notice that we've got a term with an x on this side and a term with x on this side. Remember, if there's a variable on both sides, we've got to get it on the same side so we can solve for it. So I'm going to subtract qx. So I have px minus qx equals, remember those cancel, negative c. Now, this is kind of the opposite problem of what we had up here. Up here, we had the x inside the parentheses, okay? And on this one, we had two d's when we multiplied through. What we want to do here is we want to make it so there's one x there. Well, the way we make it so that there's one x is we factor the GCF. So x is the GCF. So let's go ahead and take that out. There's an x in each one of those. If I take an x out, I'm left with a p. If I take an x out, I'm left with a minus q. And that equals negative c. I made that look like a 6 or a g or something. Okay, so to finish this off, again, we just want the x by itself, so we're going to divide by the p minus q. We're going to divide by a factor of quantity p minus q. So those cancel, so we end up with x equals c over p minus q. Okay, and I don't, oh, that's negative. Yep, can't forget that one. Okay, perfectly good way to write that one. And then the last one's kind of interesting. We want to solve this for c. This is a pretty famous formula. This comes from Einstein's theory of relativity. So let's go ahead and take a look here. We want to get c by itself. So the first thing we're going to need to do is we're going to divide by m. So we get capital E over m equals c squared. And then this goes back to something that we've talked about several times this year and last year. How do we get rid of squaring? What undoes squaring? Well, we're going to take the square root of both sides. So I'm going to take the square root of this side and take the square root of that side. So here's what we end up with. We end up with c equals big square root and then capital E over m. And there we go. Now, for those of you that are real sticklers, you might recognize we took a square root, and we've talked about when solving quadratics by taking square roots, you have to account for the fact that the original number could have been positive or negative. In this case, we're talking about energy and mass, both of which are positive quantities, so there's no way this number could turn out to be anything other than a positive. Okay, so we're in good shape there. Those are literal equations and formulas or formulae. So go ahead and rate yourself on that, and then good luck on the assignment. I did want to take a quick second to come back and take a look at example 3b and take a look right here and show you that there is another way that you can do this. Again, some really good skills that we worked on here. But again, look how many variables we've got floating around, lots of different ways to do this problem and write this problem. We could at this point right here where we have the x2 minus x1 in parentheses times m, and then the y2 minus y1, we could do this. If we want to get rid of that set of parentheses, we don't have to distribute. What we could do is we could just divide both sides by m, and watch what happens here. We get x2 minus x1 equals y2 minus y1 over m, and then look how cool this is. The only thing that we have left here to get rid of is just the minus x1, so we're going to add x1, so add x1, and those are going to cancel, and we get x2 equals y2 minus y1 over m, and then plus x1. Now, I'm not going to take the time to go through how we can turn this one into this one, but we can do the same type of thing. There's probably 3 or 4 good ways to write this one. So again, if you happen to do it this way, great. There's lots of different ways to write them. If you do it this way, awesome. Lots of good ways to write them. All right, again, good luck.